All right, so the initial caveat to this lecture is that this is actually 3 days worth of lecture for my Systems 101 class, right? And so I try to condense that down so that I can just get to the real nuggets that you need in order to be successful. And you can be successful without following this, but you're going to spend a lot more time and effort doing that. And so this is a process. Design is a process, all right? And so I'm going to talk about some things that you can do to help yourself, all right? If you use this, you will find it useful. If you don't, life is probably going to be a little more difficult for you. All right. Yeah. So we have 5 major components of the design process, right? So we have a definition, where we actually define the problem. We have analysis, where we look at what the problem really is, all right? We start to do some preliminary designs, and there's actually several different stages of the design process itself. We have construction, which means that, you know, we're actually building a final piece, and then we have testing, all right, to make sure that it does all the things that it's supposed to do. As we go through this process, as we go through this lecture, right, there's several slides on here that have a lot of information. I'm going to pick out the nuggets because, again, I'm condensing 3 days worth of lecture into an hour. So, all right, it's tempting to start here, all right? It's the human tendency that when we're posed with a problem that we will jump immediately to a solution. Oh, we could just do this. Right? And so when we gave you the initial parameters yesterday for your project, what did you all do? What were some of the things that you did? Max?
Came up with ideas for designs.
Okay. All right. What else? Somebody? Anybody? Alicia, since I know your name.
Started like building prototypes.
Okay. All right. So it's real tempting just to jump in and grab a piece of that and start working on it. All right? And now we're going to talk about why that may not be the best solution. Quote from Henry Ford. All right, and so who was Henry Ford? He's the guy who actually revolutionized the production process, right? What else is he known for? What revolutionized the production process that he's responsible for? Olivia?
The assembly line?
Okay, and what specifically about the assembly line?
That it was like individual parts being put together.
You're real close. Somebody help her out. Interchangeability of parts. Okay, he really revolutionized the whole industrial process because his thought, prior to Henry Ford's production line, everything was custom made. And so everything was custom fitted together, right? So his thing is that, hey, if I'm going to build a whole bunch of these, I need to have parts that I can take off of one and it will fit on the next, right? So the parts have specifications and tolerances, which we'll talk about later on in the term, all right? But that's what Henry Ford is most recognized for. So nearly all these features of a gasoline buggy have been planned in advance. That's the way I've always worked. I draw a plan and I work out every detail on the plan before starting to build. For otherwise, one will waste a great deal of time and makeshift as the work goes on. All right? So what he's saying there is that you want to look at the whole thing first, right? We want to step back. So we have macro level and we have micro level, right? So we have a tendency to start at the very small granular detail and solve a little problem. All right? And then the next thing we do is we take a step back and then we solve those problems, right? And things become increasingly complex as we step back a level from our zoom. All right? And this is what I call engineering yourself into a corner, in that you keep getting more complex problems because you didn't think about those when you were solving the granular detail. You step back and now you got 2 or 3 things that you have to make work. You step back, now I've got 10 things that I have to make work together. And I step back and now I've got 30 things that I have to make work together. And so it becomes increasingly more complex. And so what he is saying, in essence, is that if you look at the whole thing, you establish its scope. We talked about scope yesterday, all right, in that what is the scope of this project? And so for our project, I talked about this with the class that I had yesterday afternoon, and I'll talk it again today, is that what's the scope of your project? Well, at some place in this system, we have to have a repository for the things that we're going to sort, right? That starts the process. That is the initial input, all right? Now, within that input, we're going to have several different processes or functions that are going on. At this point, we don't know what those are, and we don't have to. Okay, we can use what's called the black box concept, meaning we know that something's going on, but we don't actually know exactly what it is, and we don't have to, but we know that something's going on. Now, the end result is going to be what? We're going to have some type of sorted materials, right? In little containers or a little platter, whatever you design, whatever you think about, all right? So the scope of our project is going to be from that initial holding all the way through all the processes, and then at the end we have another holding where our items are separated by whatever we're going to do to them, right? That's the scope of our project. So what he's saying is that if I look at it from the big picture first, all right, and I look at all the things that must be done, we'll talk about top level requirements here in just a little bit, and then we start working our way down, life will be much easier. All right. So the first step, define the problem. All right. These slides are set up for a production environment. All right. So some of it is not quite relevant to what we're doing here, but still valuable nonetheless. All right. Do we really understand what's going on? All right. What's actually happening? All right. Who is the customer? In this case, the customer are your professors. All right. We're giving you the initial parameters. You also are going to be a customer because you have a lot of say in what you're going to do. All right. So rather unique in that aspect. All right. But we're going to be interacting with the customer to determine what high-level solutions are required. All right. As I stated earlier, humans are just predisposed to grab onto a piece of something and solve that little problem. All right, we are predisposed to do that. All right, and so we have to resist that urge to jump in and solve one little problem, and instead we want to step back and look at things in its entirety first. The last little thing I like there, the easy thing is to do what has been done before. All right. And change, people and organizations are resistant to change, right? My challenge to you, and I talked with this yesterday with my students in the afternoon lecture, is think outside the box. Try to do something different, all right? Show us how innovative you can be, all right? Because, yeah, anybody can program a color sensor and be like, yep, I can get red, blue, and green. Anybody can do that, all right? Last term, we had people who did a sort by weight, all right? And when they proposed that, we were all kind of like, yeah, that's going to be dicey, all right? But they made it work, all right? So that's what we're looking for. We're looking for you to show us some innovation.
Can I jump in 1 second?
Yeah, absolutely.
So one of the things, just as a practical example, this why big companies find it hard to change. There are some big companies that do this especially well, and for example, Honda, one of their core design strategies is to avoid limiting themselves on the number of options that they're exploring as long as possible. So they continue to explore many possibilities in parallel as long as possible, and then, eventually they have to make a cut and say, okay, we're gonna go this route. But that's something that you can, you can practice with this project. You guys may initially in your brainstorming session say, I think we should do it this way, and somebody else says, what about this way? There's really no reason that your team can't pursue both of those in parallel and see which one works better. So, innovation is not just a product of like being the idea person and coming up with creative ideas, but it's a product of putting in the effort to try out your ideas. So that's thing number one. And thing number two is this interaction with the customer. We have intentionally made the requirements too vague for you to actually fulfill. So it's a requirement for you guys to like physically come to us and talk to us and say, we think that you meant this by the requirements. And then we're requiring you to write out that. And we'll have this interaction back and forth to kind of model what you would do in an industry session. Because your customer many times is not an engineer. They don't really know what they want. And they'll tell you what they want. And probably that's not exactly what they really need. So you'll have to have this back and forth. And defining these requirements is making sure that you're building the right thing. Because even if it's the best thing ever, if it's the wrong thing, then you fail. So those are my two.
Don't steal all my thunder.
Sorry.
All right, so yeah, that brainstorming process is about throwing out any idea. And you can't just initially dismiss anything. All right, just to kind of caveat onto that. So yesterday when we had the people sorter, it made a list, right? Right? What is the harm in having a wild idea out there? There is no harm. All right, and in fact, the synergistic effect of that is that somebody else sees that and they have this idea that, oh, I got this idea, right? And then as a group, you start talking about that idea and then you get a lot of spurs that come off of that, right? So that's part of the brainstorming process, which is outside of what we're talking about today, but still good stuff. All right. So the system design process practice, all right, again, what is it that the customer wants? And I've got some slides that kind of talk about this. Dr. McClure kind of stole my thunder there in that the average customer really has no idea what they really want. They've got this picture in their mind of utopia, right? But they don't have any real concept of what it takes to make that utopia happen. And a lot of times they come to you with a thought that really is not practical. All right. All right. Do your research on the topic. Interview the customer several times. All right. This is a back and forth process, right? Especially in production, this is an ongoing. You are having daily conversations with the customer, and you're continually evolving the requirements that they need, because again, in most cases they don't really know what it is exactly that they need or want. All right. Research means that I'm not only talking to the customer, but I'm researching the industry that this is in, right? I'm gaining a full breadth understanding of what's going on within that industry, within that segment, so that I can understand where the customer's coming from, and hopefully even better than the customer does. All right. So again, because the customer doesn't really know what they want in most cases, sometimes they do, but most cases they don't, all right, we have to reword that, all right, into this thing called top-level requirements. All right. What are top-level requirements? Requirements are the things that it must do. All right. So in your case, it must, at this point, the top-level requirements are, you must sort things by two different methods, right? That's our top-level requirements at this stage. As we go further through this process, what's going to happen to those? Well, your top-level requirements might expand a little bit, but you're going to have other requirements that fall underneath that that are going to get bigger and bigger and bigger, and you're going to find more and more and more. All right, develop several alternatives or concepts. Again, this is that brainstorming phase where we're looking at what can we do to actually answer the requirements that the customer has given us. All right, we're going to use analysis and find out which of these is the best answer. And we might have 2 or 3 that make that cut. All right, and then again, we're going back and forth to the customer to find out which one is going to best satisfy what they need. All right, the system design process. Definition, probably one of the most important. If you don't fully understand what it is that the customer wants, how can you design something that they need? All right. The analysis section, all right, analyzing the problem, expanding and refining the requirements. And again, this is ongoing. As you go through the design process, you're continually, perpetually refining those requirements. All right. Discovering alternatives. Again, we're reviewing this with the customer. All right. It's a two-way street. We're having conversations on almost a daily basis, making sure that we're meeting their requirements. All right. Once the customer agrees, then we can move on. So that for initial definition, the most important thing that comes out of that is we have defined clear requirements. All right. And then when we're creating or we're doing our analysis, all right, the final outcome is that, hey, the customer has said, yeah, I'm good with this. All right, after the customer selects that, all right, then we get into a preliminary design. All right, so we're making something. All right, now preliminary design, and we'll talk, there's a couple slides down from here where we talk about some of the design concepts. So last night you were charged with making what? Some type of cardboard design to show one concept, right? Well, once we have a preliminary design, all right, then we start refining that, and we keep refining that. And we're going to talk about in a later lecture the iterative design process. I have one slide where I talk about the iterative design process. There are several iterative design processes out there. There are 6, 7, 8, 10, I don't know. There's a bunch of different takes on the iterative design process. They're all somewhat similar, all right, but if you work for a major corporation, they probably have their own iterative design process that they have, named, all right? So then we get down to, we've got a detailed design and we're starting to create it, all right, and then we're going to do testing and analyzing. Does it actually do all the things that we said it would? All right, and you're going to do all of this, right? So you already started off with a concept, all right, and you're going to continually refine that concept, and it's going to get more detailed, more fleshed out, all right, and then you're going to get to the point where I pretty much have it all together, and now we're going to start testing it to make sure that it does what we said it would do, all right, and then of course the last thing is deliver to the customer. All right, just a flow diagram. All right. So again, just as I said, different organizations have different variations on these phases. All right. Most organizations will customize it to fit their niche, what their market is, what their industry is.
And just a quick note on the formal review. So throughout your classes, we're going to make you do increasing level of documentation in your lab reports. Please don't view that as, oh, this is just busy work. Why is my instructor making me capture all these screenshots and take all these pictures? Why do I have to do that? You have to do that because that's what you're going to have to do in your job to clearly communicate the technical details to your boss and other engineers and the customers, etc. So just quick comment on these reviews are really important, and they also require good skills at creating figures and making high quality technical documents. So,
Yeah, and it is a daily conversation with your customer. Okay, so I have two slides that talk about the V diagram, right? And so this is probably the most important slide in the whole thing. All right, actually this one and the next one. So what we want to look at when we're first designing a system, when we're thinking about the designing of a system, we want to look at, okay, what are our top level requirements? All right, well those top level requirements as they sit right now are what? It's to sort by two different methods. We haven't fleshed those out. You're going to, all right? So you're going to select, maybe you're going to sort by color, maybe you're going to do sort by weight, maybe you're going to do sort by shape, sort by size, whatever, all right? So those requirements are going to expand as you start developing this. Once we understand what those top level requirements are, then we start looking at subsystems below that. All right, so top level requirements are the whole thing must do this. But within our system, we're going to have what? You're going to have subsystems. So in my class that I had yesterday, I talked about some of the things that we must do. All right, so number one, when we talk about the scope of our project, the scope is at first we have this initial holding area, right? So that's a subsystem. All right, so we're going to have that. And there will be requirements for that. All right. Then from that initial hold system, we have to have a way to actually feed parts at a set rate, right? That's going to be a requirement that you get later on too, because we're going to talk about how fast it should do something. You're going to have that requirement. All right. So now we fed something out, and we've got to transport it somewhere. There's another subsystem. All right. So now we're going to have some type of sorting, whether it be mechanical, sensors, or otherwise. Those are each subsystems. And then we have to transport from those subsystems onto other subsystems. All right? And so by looking first at the scope, looking at those top level requirements, and then we look at each of those subsystems and say, okay, what are the requirements for those subsystems? And then guess what? Each of those subsystems are going to have subsystems underneath them, right? Make sense? All right? And so we keep going down until we get to that granular view. All right, the next slide is actually a little better than this one, but we'll get there. So now I'm down and I'm doing the actual granular thing, right? All right, so now I'm addressing that granular thing. Now this is, human tendency is that we want to first just jump in on that granular view and start focusing on one little problem. Because that's what we're taught to do from kindergarten, is to solve one little problem at a time. Well, in engineering, that's not necessarily the best route. So once I've got that, then what do? I'm going to test that granular feature, and then I'm going to start building back up. And so I'm going to test the individual thing, and then I'm going to step back and say, okay, now the thing that feeds that, is that working with it? And then where does it go from here? Does that work together? And then I'm going to keep stepping back, all right, until I get all the way back out to whole system. So here we go. Feasibility study, concept of operations. This is where we're looking at system-wide, you know. Is this something that we can do with the resources that we have? What are the requirements that are required? What are those top-level requirements? We're going to make a high-level design. All right, so again, we're looking at what are the major pieces to this puzzle. Then we start breaking it down into more detailed things. All right, and then we get all the way down to the bottom where we're working on that granular detail. All right, then here we go. We're testing at the individual level, the unit level. And then we're going to go back up and we're going to look at the integration of those individual things with other individual things as a subsystem. And then it just keeps climbing, right? Until, again, we get all the way back up to system validation. Does the whole thing work the way that it's supposed to? design is a process. Right. As Dr. McClurg said, emphasis should be on solving the right problem for the customer. How do we solve the right problem? In that we understand fully the requirements, the top level requirements. And we've worked with the customer on a daily basis to continually refine what those are. Design is often multidisciplinary. No matter where you go and what you do, you're always going to work with people who have different skill sets than you. That is a fact of being an engineer. All right? So this class is a great example of that, because you're going to have what? You're going to have electrical, you're going to have mechanical, you have programming, all right? Some of you have strengths in those areas. Some of you have very little knowledge in any of those three areas, all right? But everything to do with a system design is multidisciplinary, all right? You have people with different skill sets that are all working together. So what that means is that we must be able to communicate to those people. And a lot of times this is where we have problems, because we're each thinking of something different. We're not speaking the same language. We've already talked about requirements. Early focus on the system. Again, starting at that system level, all right, and then working down. Flows from system design to component level design with increasing complexity. And then a good systems analyst must talk to and understand everyone's skills on their team. So team leaders, understanding who has what skills that they can bring to the table. And as I told my class yesterday, we have some people that have some mad CAD skills, right? We also have some people who've done some programming for Arduino or Raspberry Pis. So what we ask is that for those people with those skills, if you're highly skilled in CAD, I would really rather you focus on the mechanical design or the programming design and be a backup for the person who's actually working the CAD stuff. Because if you do what you already have skills in, what are you gaining? Very little. All right, so team leaders, keep that in mind. If you've got somebody with mad CAD skills, that's a great resource, but they should not be doing your CAD design. All right, especially for this program, for this process that we're doing. All right, as I've said probably 10 times already, continual expansion and refinement of requirements. As we continue to get more and more detailed in the process, we're going to continually refine those. All right. As you work through those, you'll probably find some things that weren't disclosed early on. You know, and the example there is that, oh, the car must go X amount further than what we initially thought. Well, the ripple effect is that, what? We had to make a bigger gas tank. Well, if we make a bigger gas tank, then what's the ripple effect of that? We've got to be able to place it in the car. So we had to move other subsystems around, okay? Again, so this is an example of engineering yourself into a corner, right? If you don't think about all these things up front, then you wind up mid-process having to back up 5 or 6 levels to be like, oh man, now how am I going to make this work? I beat that horse to death. Use of special analytical techniques like modeling and simulation, or building prototypes. That's what this class is about, making prototypes until you get something that works. So this is really on, they start off with low fidelity prototypes, right? So they started with making computer mice and electrical vehicle charging stations, right? Well, their design process starts with a low fidelity. They make something out of foam to say, you know, hey, this is kind of what it's going to look like. And again, if you show somebody a drawing, most people have difficulty taking that two-dimensional thing and making a three-dimensional picture. All right. So again, this slide set is for production, right? The sooner that we figure out that something is wrong, the less money and resources it costs. For you, it means less time, all right? So if I'm able to find an issue when I'm doing requirements, it literally costs nothing, right? It's a one-to-one deal. I can fix something and it doesn't really cost me anything. If I get into the point where I'm starting to make designs, all right, it becomes a little more expensive. It's still not terrible, but it becomes more expensive. If I get beyond that initial design, that prototyping phase, and I get into something that's much more detailed, the cost went up tenfold, all right? If I then get to the point where I'm doing testing of an approved design and I find out that we missed something, 20-fold, all right? And then it just keeps getting more and more expensive, all right? So the relevance to you is that this is all time. For you, it's not about money, it's about time. So the more time that you spend up front looking at things and trying to make sure that you're covering all your bases, the better you're going to be. Because as you get 6 or 7 steps in, and then you realize that, oh, we missed something, all right, now you've got to backtrack, all right, and it costs you time, lots and lots of time.
One small comment on this one. Being a good engineer also takes a good amount of humility too. So you will definitely find problems in your career. You'll find problems all the way right up until the end, and you may need to go back. So don't be so like hold on to your ideas so dearly, like they're a part of your soul or something. Your ideas are there to be tested against what works and what doesn't, and finding an error is really valuable. So if you find an error at the acceptance test stage, that's huge. It could have potentially cost people's lives after, like if you didn't catch it then. So that's really important. So I actually find this sometimes even with our seniors. So there's this like fallacy of sunk time, where you sink a lot of time into one direction, and you sort of get emotionally attached to that idea, and then when later on you discover, oh no, this isn't the right way, it can be really hard to like let go of that and go a different direction. So just practice now being open to the fact that you might have to do something different, even though you think this is a really good idea, because that's the way things are.
And another way to look at that too is that even if it gets all the way out here and I catch it, right? If I fix it here, it's still only costing me 50 times. If I just say, oh, it's okay, and it gets out here, well, it just quadrupled the cost, right? So, but again, the sooner that we catch an issue, all right, the less it costs us in time, resources, and money. All right, we're going to skip that. All right. These next few slides are wonderful. All right, how the customer said he wanted it. How the project leader understood it. How the analyst designed it. How the programmer wrote it. How the project was documented. What operations installed. How the customer was billed. And then how it was supported. All right. What the customer really needed. All right. A picture says 1,000 words. All right. And they really do. What do you see there? Failure to communicate, right? What were you going to say, Max? You're good. Say it.
They're asking for more than they need.
Maybe. All right. But communication is key. We need to be able to understand and then communicate back to them. We have to be speaking the same language. Good requirements have to be measurable. If they're not measurable, all right, it's not a good requirement. All right. All right, here we go. Requirements are either mandatory or desirable. All right. Mandatory requirements are mandatory. They must do this, or it shall do this. Desirable ones, all right, or it would be nice if it could do this, all right. A lot of times when we're doing a design, we actually can build in some of these more desirable things at no extra cost, right? Clear, unambiguous, and not confusing, expressed in the customer's terms and jargon. So whatever, and again, so I talked earlier about researching in the industry that we're going to be doing this in, right? We need to speak the same language, all right? And so if we're not speaking the same language, then that series of slides with the different swings in it, that's what we're going to wind up with, because we're not doing the same stuff. We're not talking the same things. What I say and what they hear are different. All right. We're running out of time. All right. Requirements must be SMART. Specific, measurable, attainable, as in achievable, actionable, and appropriate, realistic, and we want them to be time-bound, if possible. All right. So you're going to have some time-bound requirements, right? It must do this. It must process so many pieces per second, per minute, whatever. All these slides are on Moodle, by the way. All right, requirement writing. So when we write our requirements, there is a formatting system for this. All right, and so top level requirements are going to have their major heading, right? So 1.0. Sub-requirements underneath that then are going to be indented, and then sub-requirements of that sub-requirement are going to be indented, right? And then we have a specific numbering sequence so that when we look at this, we can call out specific requirements to the things that are addressing those specific requirements, all right? So as you do your reports and stuff, this is going to be important for you because you need to be able to call out specific requirements. All right, tasks, not that important. All right, specifications. Specifications are the things that meet those requirements. All right. And we're there. Questions? How many people are just totally overloaded? 2 people. Okay. All right. Again, 3 days worth of lecture in 50 minutes. It was fast, it was furious, I skipped. There's actually almost 200 slides that go into this. I showed I think about 40. Right. A lot of information. Ask questions, that's what we're here for. Yes, sir.
So we're meeting back here.
Yes, at 1 o'clock we'll meet right here.
Yeah, for the first week or so, we'll just always meet